everyone. So today again we have one more very interesting topic, which is dynamic programming. It is one of the popular topic in data structure and algorithm, which is sometimes, most of the time I would say rather, is very difficult topic to understand. I see many of the people out there, they have an interview and a question is asked, and from the mindset of an interviewer, they're expecting a DP solution, but we end up in making some other solutions which is not optimized. So as part of this demo, I would focus on again the fundamentals, the basics of dynamic programming, and then I will also talk about high level problems, data structures problems that exist in this dynamic programming world, and then we will understand how and which way for a developer, for a person who has a problem in front, can easily find out that okay, this is a dynamic programming problem or not. So let me quickly go to the session, and we'll start something with a very basic understanding of what is dynamic programming. I hope after this session you will understand, whenever you have been given any problem, it will be easy for you to find out whether can I put a dynamic programming solution here or not. Would DP solution is a worth solution for this problem statement or not? So all these are going to be very easy for you when we solve this, when we understand the session completely in detail. So let me take quickly to the dynamic programming session. So the very first thing which always comes in mind is that we have to look, every person has to look, what he has to look for, if the problem statement which is upfront in front of you, it can be broken into smaller overlapping subproblems where solutions to the subproblems can be resumed to multiple times. So what does it mean? So it simply means that the whole problem, like you have a big problem, and if you think the solution of that big problem is nothing, but it is collection, or it is substitution of all the sub problems. So meaning the whole problem can be broken down into smaller overlapping subproblems where solutions to the subproblems can be reused multiple times. Meaning if you're solving a solution for a small problem, the same solution is used in other part of the same other overlapping subproblem solution, and that way you are doing a lot of optimization, memoization in that. So if that is the case, if you think that problem statement can be broken into smaller, and you are reusing multiple times the solutions of subproblems, that tricks gives you the technique that hey, this is the way, this is something where is the dynamic programming, okay, is something that can work. So what is the best optimal way to solve a subproblem? This is point one. Or if you see the same function or computation being repeatedly called with the same inputs during brute force, it is a sign of your DP. Okay. So for example, I just quickly explain you very simple example, Fibonacci series, right? So Fibonacci series is a very popular problem. We can solve it in a brute force way. I mean, we can create a recursive function, then we can say return fib n minus 1 plus fib n minus 2, and then we just need to handle the edge case where the recursive function will terminate, right? So if n less than equal to 1, we return n. That's pretty straightforward. But if you see here, return fib n minus 1 plus fib n minus 2, don't you think that there we are computing those things again and again? Because n minus 1 will eventually, one once it goes inside, it will again do n minus 2 in the next iteration, next recursive call. So n minus 2 is calculated 2 times. So this is one of the best case where you can solve this Fibonacci solution using DP, right? So Fibonacci series is one of the example where you can talk about overlapping subproblem solutions. So you can avoid redundant calculations by using DP here, rather than recalculating Fibonacci numbers again and again. So time complexity of any recursive solution, it's always 2 to the power of n, where n is the number that you got in. But when it comes to your DP solution, it reduces the time complexity from O to the power of n to O to the power of n. So yeah, that is overlapping subproblems. So let me quickly go to other clue that we can get always from a problem. That is called optimal substructure. What does it mean? Optimal substructure is a key factor wherein the solution to the problem can be built from solution to its sub problems. What does it mean? Mean if you combine solution to smaller problems, giving to the solution of the larger problem, that is where you say optimal substructure is achieved. For example, knapsack, right? We all know what is knapsack. So in knapsack problem, what happens? You've been given weights and values of the items and maximum weight capacity, let's say W. Find the maximum total value that can be carried without exceeding the maximum capacity, that is W. So this is a knapsack problem. So in a knapsack problem, the optimal solution depends on the decision to include or to exclude an item. And the problem is solved by building up smaller subproblems. So what we do actually, we combine solutions to smaller subproblems to calculate the maximum value for each weight limit. We will do it in a separate session, but just on a very high level, knapsack problem or something which is similar to knapsack, where you have weights and values to them and you have to decide whether to include or exclude an item, is something that can be a key factor or a deciding factor if you can choose DP or not. Next, decision-based problems. What do you mean by decision-based? Again, optimal substructure or decision based, they're more or less same, but when you say decision makes, you pick or not pick at every step. For example, let's say, let's say there is a thief is planning to rob houses along a street, all right, and each houses has a certain amount of money, but robbing two adjacent houses triggers an alarm, right? And let's say the question is, find the maximum money the thief can rob without robbing two adjacent houses. So in that case, you see here, there is something which forced the robber to take a decision whether to choose a particular house or not choose. So situation is like this. This is again something which is a clue that house robber problem, the decision to rob a house depends on whether the previous house was robbed or not. It's all about DP. So DP is the best solution here where you have decision based problems. Okay, let me quickly go to the next clue. Problem with constraints. What does it mean? Problem with constraints. So problem with constraint, it simply means that problem asks for the maximum and minimum or count of ways under specific constraints. Like, let's say, no adjacent element, at most x times, sum equals y, and all these, right? So for example, let's say the problem, given a set of integers, determine if it can be partitioned into two subsets such that sum of the elements in both subsets is equal, right? Now, sum equals, or it could be let such that sum of the elements in both subsets is at most x time, and something like that. So if you have constraints in your problem, that is again a clue factor. I mean, that is again a clue which you can take as a clue that you can do DP as a solution. So partition equals subset, ask whether we can partition an array into subsets with equal sum, which involves constraints on element combination. We will take all these problems when we do the real coding exercises, right? But I'm trying to explain you on a very high level how and what are the triggering point for a person to decide whether DP is the solution here or not, right? So that is the way, that is the reason why I'm trying to cover, I will try my best to cover here all those things which would be the deciding factor that if you can choose DP or not. Next, recursive structure. So you already seen, the very first thing, recursive structure. For example, let's say the problem can be expressed recursively by breaking it to smaller versions of the same problem. So for example, let's say Fibonacci sequence, we already saw that. So the value of fn depends on fn minus 1 and n minus 2. That is the recursive solution. But DP improves this recursion by storing intermediate results. Okay, we call it a memoization. We'll see that in later when we do the real code. So recursive structure, wherever you have some recursive structure, wherever you have something which is already being calculated and repeated many times, you have a recursive structure here. For example, longest common subsequence. What we are doing here, given two strings, find the length of the longest common subsequence. A subsequence is a sequence derived by deleting some or no elements without changing the order, right? So you're not changing the order. A subsequence is a sequence. You're making a sequence which is derived by deleting some or no elements without changing order. So that is subsequence. So if you have to find the longest Common subsequence, this is something that can be solved recursively, right? So this is also one of the case where DP is the solution. Problem with multiple states. So let's say we have something which is called, I would like to give a very simple example. Let's say you are in a top left corner, okay, of a grid, and you need to move to the bottom right corner. You can only move down or right. Find the number of unique paths to reach the destination. So what is here? You have problem with multiple states. The solution depends on multiple variables. For example, indices, remaining capacity, previous decisions, and all that. If that is the case, you can have DP as a rescue for the solution that you're targeting. So your problem has multiple dimensions to track, like index plus current state, remaining sum, previous number, etc. So that is where the DP can be a solution. Next, counting problems. So for example, let's say what you need to look, for example, if you have a problem, interview problem which is given by an interviewer, and now when you read the problem you get a smell of, or let's say you get a sense of, count all possible ways to achieve something. For example, let's say you can climb one or two steps at a time. Given an step, find how many distinct ways you can climb to the top. Again, what is this? You have to count, right? So that is again how many ways, often involved, something which is where DP can be the best. So climbing stair problems is one of the popular common problem for using DP can be solved. Subset combination problem. So over here, when we talk about subsets, so let's say given a string S and a dictionary of words, determine if S, the string, can be segmented into space separated sequence of dictionary words. So what to look for? The problem involves finding subsets or combination of elements to satisfy a condition, right? So if that is the case, you look for a problem which involves finding subsets or combinations of element to satisfy a condition. This is where you can always have DPS as your friend to solve. So for example, word break, okay, using DP to determine if a string can be segmented into dictionary words or not. If that is the case, this is where your DP comes in rescue. String and subsequence. Okay, string and subsequence. So subsequences, as you already saw that longest palindromic subsequence, longest common subsequence. Given a string, you have to find the length of its longest palindromic subsequence. A subsequence is a sequence derived by deleting some or no characters without changing their order. Okay, so if that is the case, this is where DP can always fit and best give you the best optimized solution. Optimization problem. Okay, what do you mean by optimization problem? So when we say optimization, so what does it mean? It's like problem asking for maximum profit or minimum cost or shortest path. Wherever you find all these things, this is a signal that you can use your DP as a solution. Okay, so maximum profit, minimum cost, shortest path, and all that. These are all DP. Okay, whenever you have anything, any of these keywords, in your question, let's use DP for there. I would say more practice you do with more questions, it will be easier for you to just get a smell or get a sense of if it is a DP solution or not. Let me quickly summarize everything here, what you have to memorize. Well, look for repeated substructure. If brute force seems to repeat calculations, DP is your go-to. Keywords, maximum, minimum, count of ways, length of, optimal, shortest, longest, least. All this, they are giving you the clue for DP. Recursive nature. If solving the problem involves, if solving the problem involves breaking into smaller self-similar subproblems, what does it mean? It is recursive problem. Constraints. If you need to make decisions under constraints or consider multiple paths, that is where decision making capacity under constraint is where you have your memoization tips. It is giving you the DP as a solution. Storage. If you can identify overlapping subproblems that can be stored in an array or table, meaning solutions of the overlapping subproblems, if you're storing somewhere, you can store them for efficiency and then later reuse it without calculating it again. This is where something which also signifies DP can be used as the solution. During an interviewer, if you're unsure, try to write a recursive solution. Check if subproblem result can be used, overlap, If constraints or decision affect future choices, think about whether storing intermediate results can avoid redundant calculations or not. And that's pretty much all for so that is pretty much that is so we have to understand all this. So that is pretty much all from this side. We will see in real all these patterns in real with some of the problems when we solve this. I would like to cover both brute force. We'll understand whether it is an overlapping, it is an optimal sub problem structure, path, maximum, minimum, shortest, count, wall. We will see all those clues and try to correlate what we have understood here, right? So see you in another video. Thank you very much. Bye.